So this evening, everybody, Professor William Grundy, I think that is correct, is that not right? A planetary scientist at the Lowell Observatory in Arizona. He studies outer solar system, studies the outer solar system via observational, theoretical, and laboratory techniques, as well as direct exploration via space probes. Very lucky, not a bad job to have, I would say. And Bill Grundy has been involved with NASA's New Horizons mission since its inception more than 20 years ago. So can everybody please put their hands together and welcome Will Grundy. Thank you.
Thank you. All right, so you've been staring at my title for plenty long enough. I should explain what I mean by the third zone of the solar system. So this is kind of a cartoon view of the solar system. And I like to divide it into three zones. The inner zone is small rocky planets and planetesimals, and I'll define that in a second. Once you get far enough away that you can form solid water ice, oxygen is one of the most abundant elements in the universe, and oxygen plus hydrogen, which is the most abundant element, basically makes the most abundant solid, and you can start to build much bigger things. And so you get this zone of giant planets. And once you get above a certain size, they attract a lot of gas from the solar nebula, so you can grow truly huge things. But those giant planets originally formed from planetesimals, and there's lots of leftover planetesimals both in the inner solar system and in the far outer solar system. And this third zone of the solar system out beyond the giant planets is what I'm going to be talking about exploring with New Horizons. And if you like alien, exotic, extraterrestrial geology, that's the place to go, because there's more surface area, real estate on objects that are bigger than 100 kilometers in size, so not small objects, than there is in the entire rest of the solar system combined. So counting all of the terrestrial planets, and I'm counting all of the surface of Earth, including the bottom of the ocean and everything, all of that adds up to less real estate than what's out in that third zone. And we've barely scratched the surface, so there's plenty of exploring to do. Now, okay, I used the word planetesimal. I better define that. So a planet is when you make something large enough to be spherical and differentiate itself and have geological stuff going on its surface, and maybe have an atmosphere and so on and so forth. But a planetesimal is this sort of key building block size where you've become big enough to be held together by gravity. So you can imagine dust particles. Those are not planetesimals. But if you stick enough dust particles together that you overcome, that they're held together with gravity and not just, cohesive forces like electrostatic forces or something, that's when you've got a planetesimal. And there's lots of them left over in the solar system. The process of making planets wasn't super duper efficient. All right, so let's move on to New Horizons. This is the trajectory. So the launch was back in 2006, and we did a Jupiter flyby to get more speed in early 2007, and then encountered Pluto, which is the yellow orbit, and that was in summer of 2015. And conveniently, we encountered Pluto right as its inclined orbit was crossing the plane of the solar system. And that one made it easier to get to because we're launching from in the plane of the solar system and so on. But it also meant that after the spacecraft had gone past Pluto, it was still in the plane of the solar system. And that's where the most of these small Kuiper belt objects, or KBOs, or sometimes I'll call them TNOs for trans-Neptunian objects. I'll apologize in advance if I'm chaotic with that, because I just don't even think. But we encountered one of those in New Year's, well, the end of 2018, beginning of 2019, in the form of Aracoth. And I'll talk a little bit about both encounters, since they kind of bookend the size scale of objects out in this third zone. So I don't want to spend a huge amount of time on Pluto because I want to leave some time to talk about Aracoth, but these are kind of what I think of as the crown jewel data sets for Pluto. So we got color imaging, we got black and white imaging, which we call panchromatic because it covers the full range that the human eye can see. Infrared compositional maps like the bottom middle, where you can distinguish what different landscape are made out of. Some high phase observations looking back at the dark side of Pluto, where you can see the glow of sunlight through the haze in Pluto's atmosphere. What I want to do is, and I'm going to have to, the zoom window landed on top of the window that I wanted to use, so I'm going to get it back to it. What I want to do is show you a few of these data sets just so you can kind of get an appreciation of how juicy they are. So this is that Pluto color image, and it's about 5,000 pixels wide. So my screen and your screens aren't doing it justice. But what we can do is we can immediately see the immense diversity of the landscapes on there, and we can zoom in to get a more full appreciation of what kind of scale we have. So we've got this giant glacier that's slowly convecting like a simmering pot of oatmeal, maybe on a time scale of 100,000 years up to maybe 1 million years to overcycle. And really rugged mountains off to the left, which are perhaps being buoyantly supported in the glacier to some extent because they seem like they've kind of moved around. It's even more obvious up here where you see this jumble of what looks like icebergs. On the other side, you can see the glacier is being fed, and I wish my mouse pointer worked so I could point it out, but near the center of the screen, you can see a sort of a valley-shaped glacier that's flowing from the rugged terrain on the right down into the smooth expanse of nitrogen ice to the left. There's another one of them up here. There's a whole series of these, and so somehow or other, Pluto is depositing nitrogen ice on this rugged high terrain, and it's glacially flowing downhill, so that's kind of fun. You can see that it gets amazingly rugged over here. We were calling that dragon skin because we didn't have a really good name for it, but it looks like it's probably analogous to the penitentes that you see in alpine regions where the sun is sublimating and preferentially carving valleys into the ice. This is mostly made of methane ice. You can see huge tectonic features where there are big cracks in the ground. You can see impact craters, but you also see craters like this little clump of them in the center of the screen now that are obviously not impact craters because impact craters don't just form neat little rows and clumps like that. So something else is either falling into the ground and sinking below the surface or maybe blasting out. And this apparently is still geologically active today. Up here, you can see all of these valley networks as if there's some kind of drainage going on the surface. And there's maybe an even more obvious one up here. You see the crater in the center has had its rim breached, and there's sort of a valley heading up to the north from it, up towards the North Pole. We don't really know of anything that could be flowing as a liquid currently at Pluto's surface conditions, but maybe the conditions were different over geological time, or maybe it was flowing as a glacier, or maybe it was flowing under a glacier. Just an amazing diversity of landscapes, these reticulated kind of terrain in there now, craters with methane ice, whitish methane ice on the rim and dark red organic materials down in their floors, these tectonic cracks where the surface has pulled apart. Okay, well, I could spend all day poking around on this image, but I want to show you a couple others. So this is a strip of black and white images that we have a camera on an 8-inch telescope on the spacecraft that can take a 1K by 1K image, which would be a pretty low-grade webcam nowadays, but of course this was launched in 2006. But we just banged off a series of those images while we were scanning another instrument across the surface. And so they're 1,000 pixels wide, and so you can get kind of a tour across the surface. And you can see all of this interesting geology. You see layers in the crater walls that hint at different things having been deposited in multiple sequence of time. These ripples that sort of have a dune-like appearance. Then these really rugged mountains, and then now into the glacier that's slowly convecting. But you see patterns that look a lot like dunes, and I'll talk a little bit more about those in a bit. Wind streaks, which are consistent with dunes. But the character of them changes slowly over time as you're across space as you're scanning through this sequence, and now they're looking a lot more like dimples, and eventually they start looking like pits. And then you start seeing these bigger pits with dark floors, and the character slowly changes. So there's a lot of processes going on here. It's really a very dynamic environment with things happening on lots of different timescales. Basically, exactly what you would expect to see in a planet, as opposed to, say, a planetesimal or a small body that's geologically done. All right, so let me get rid of this. Oops. Zoom windows pop down, get in the way. Okay, so that's the crown jewels for Pluto. And the main results that we get from Pluto is that there's just this incredible diversity of processes that are going on a wide range of timescales. And a lot of these are still happening today. And Pluto is pretty far from the sun. I mean, its average distance from the sun is 39 times as far as the Earth's average distance from the sun. And sunlight falls off as r squared. So the average sunlight that it gets is like a watt per square meter, where we get 1,300 watts per square meter on Earth. And yet it's the sunlight that's the main source of energy that's driving this. And so, how can you have all this activity going on with such a feeble energy input? And the answer is that it's these ingredients, these volatile ingredients, things like nitrogen ice, methane ice, carbon monoxide ice, that are weakly held together. And so it doesn't take a huge amount of energy to mobilize them and send them doing their stuff. And really, it's having a material that can change phases, turn into gas, go somewhere else, get redeposited, and then flow back down again, that enables all of this interesting geology. And the same thing is true on Earth, where we have the oceans, and you evaporate water into the air and you drop it somewhere else and you carve the Grand Canyon. It writes itself large on the landscape. So let's move on to Sharon, which is pretty much a planet in its own right. Although it's perhaps not so active anymore today, it looks like it was quite active early in its history. There's sort of two distinct provinces on the encounter hemisphere that you can really see in the upper left. There's sort of a smoother southern hemisphere that looks like it was resurfaced more recently, and a much more rough that itself looks like it was resurfaced but earlier. And so this kind of suggests two separate episodes of resurfacing, and that's not a crazy thing to happen, where early on it would have melted or partially melted, and as that water is freezing, it chokes off the there's a burst of geological activity because it expands as it freezes, so it pulls apart. But then once it's frozen, it's less able to remove the internal heat, and so it can then remelt and have a second episode. And I guess I won't spend the time to poke around in these, but they're just as great fun to go. It's well worth your time if you like looking at exotic landscapes to grab these images. They're all public. You can get them from the NASA website or elsewhere. So the main results for the satellite are earlier geological activity that's probably mostly tailed off today. The dark red pole is kind of striking, and that's I've hypothesized that that's due to gas that's escaping from Pluto getting cold trapped in the cold pole and then processed with space radiation before it comes back into the sun in the summer and all sublimates away. There's fewer craters than were expected, and that's going to become important later for Aracoth. But it basically says that there's not that much stuff flying around out there to crash into Pluto, and which means that things that are out there are less damaged than you might otherwise expect them to be. And so you can learn more about their formation conditions from looking at them, the small bodies that are still remembering their shapes that they formed with. There's the 4 small satellites, which were 2 of them discovered before the launch of New Horizons, and 2 of them that were discovered while New Horizons was on its way to Pluto. And we didn't find any more than that. But they're all very bright, clean water ice and spinning crazy all different spin axes spinning very rapidly. It looks like this is the aftermath of a giant collision, just like with the Earth-Moon system, except that we didn't end up with any small satellites here in the Earth-Moon system. We might have had them early on, but they're more easily perturbed away when you're closer to the sun. And so probably if there were small satellites, they crashed into the moon or crashed into the Earth a long, long time ago, and we've lost all geological record of them. So all of this frenzy of science that's been going on since the New Horizons flyby 6 years ago has been distilled into a new textbook that just came out a couple of months ago, and the first printing sold out like instantly, because academic textbooks, they don't print very many of them. So it's not like it's racing up the bestseller list. It's just that they only printed one pallet worth of books and they sold out. But they did go to a second printing. So you can still get it if you want it, but it's pretty dense stuff. Who knows when the next update is going to be needed? Probably not until that orbiter happens, and we'll see when that happens. But what I want to show you is just to give you a taste of the science that's continuing. People are still writing proposals, doing new projects, working with the data, and that'll continue for decades probably. And so I want to show you a couple of recently published results, just to give you a taste of how people are learning more about the system. And so the first one is I think a useful lesson, because it's something where it looks very familiar, but the mechanism turns out to be totally different. So the leftmost picture is the Alps on Earth, and we're very used to seeing snow up in the peaks and warmer down in the valleys. And then the middle picture is some mountains that are on Pluto, and they also have bright peaks. And the right-hand picture is a map of methane ice. So basically showing you that those peaks are covered with methane ice. So, okay, fine. Looks like the Alps, except that the snow is methane snow. But this guy, Tanguy Bertrand, who's now in Paris, he was at NASA's Ames Research Center a couple of years ago. He's running global circulation models, the same kind of models that you use for weather forecasting or climate modeling on Earth, tuned to Pluto, and discovered that the mechanism is really very different than what we're used to on Earth. So on Earth, it's warmer down in the valleys and at sea level, and warmer air can hold more water. And when air blows up over a mountain, it goes up in altitude and it expands and it cools adiabatically. And when it's cooler, it can't hold as much water. So the water has to come out as rain or snow or frost. And so you end up depositing water on the peaks of the mountains. I guess you probably don't have them much where you are because it's relatively low altitude, but we call them orographic storms, where a lot of times you'll see the storms, especially in monsoon season here in Arizona, they form first on top of the mountains and then they spread. But it's a very common summer storm pattern that we get here. On Pluto, it's actually warmer higher up in the atmosphere. And so that's where the methane is. But the peaks of some of these mountains poke up into the warm air, warm methane-rich air, and they're radiating to space and cooling. So they cool that air. And as a result, the methane comes out and deposits on the peaks, and the air rushes down the slopes as katabatic winds. And, so it's the net result looks about the same, but it's really a very different mechanism from the point of view of a climate scientist. So I thought that was kind of a cool result. Here's another one. This guy, Matt Telfer at Plymouth, he mapped these dune ridges in that image that I showed earlier. And of course, there's katabatic winds rushing down the slopes, and it just so happens that the dunes tend to be transverse to the prevailing wind direction that you can also see when you do the climate models or the global circulation models using the real topography. So they really do look like dunes, at least in this part of the region. So we did further analysis on that. This pink is a methane map, and it more or less maps up to where he mapped the dunes. So it really looks like methane ice sand is a good candidate. then he also did a bunch of calculations of what kind of wind speed it would take to mobilize methane sand particles. And of course, it depends on the size. If you have a huge boulder, you need a pretty fearsome wind to make it move. Also, if you have really, really small particles, the cohesive forces between them make them hard to move. So these curves show that there's an optimal size that's easiest to move, and it works out to around maybe 250 or 300 microns, which is 0.3 millimeters, which is a typical beach sand size on Earth as well. So it's not a crazy size particles. So the white curve is how fast the wind needs to be to move them once they're moving, to keep them saltating. And the dashed horizontal line is the typical fastest winds that you get from the global circulation model. So that holds together, but the blue curve is what it takes to initiate motion. So it looks like it's actually very hard to get them started moving, but it's easy to keep them moving once they're started. So the hypothesis is maybe there's some other mechanism like a landslide or something. And you see that there's a lot of methane on the steep slopes up in those mountains. And so that's a possible source that you could have landslides there, and then the wind carries the methane out a ways, but then eventually it sputters out, once the particles come to rest and they stay at rest. And so you can see that the pinkish color attributed to methane, that maps where the methane is, it kind of fades out towards the lower right of this image, out into the core of the glacier where it was starting to look less like dunes and more like pits and dimples and other odd shapes. So the last one, Pluto result I want to talk about is something that these two have published several papers on. And they were noticing that a lot of the craters look like they're kind of filled in. And you can see, especially, there's one of these tectonic cracks that looks like it's partially filled in. And there's a crater where there's sort of a breach in its wall, and it has a very flat floor with this reddish material in there. And so they're conjecturing that these are actually eruptive deposits. How else are you going to get them into a crater? You can't just flow across the landscape. Well, maybe when the rim is breached, but some of these craters that look filled in don't have breached rims. And the only way to get stuff in there is you blast it up into the air, or maybe it's dust that settles out of the air or whatever. But they're arguing for the cryovolcanic hypothesis. And where they see these things tends to be along these fractures. And so it holds together that might be a place where it's easier for something to erupt out. Here's another example where in the upper right corner, you can see that it's a relatively smooth texture right near that fracture. And then the lower map, the darker the blue, the more water ice you see. Even though it all looks dark and red, you can still see the water ice from the infrared observations. And closer to the crack, you see more water ice. And so their conclusion is that what's erupting is in fact water that probably it's liquid until it gets out, and then it flash freezes and falls to the ground like a pyroclastic deposit in a terrestrial volcano. Their scenario was that maybe there's some kind of subsurface aquifer or pockets of melted material, and the fractures give them an escape route, as shown in this cartoon. But another scenario involves the freezing of an interior ocean. And of course, as water freezes, it expands. And so it needs more space. And so either the surface has to crack apart, or the water has to get squirted out, or some combination thereof. So there's a pretty reasonable scenario to explain some late surge of internal activity from a small body like Pluto if it has an internal ocean that's gradually freezing. And, just to back up a little bit, all of these fractures are really quite fresh looking. You don't see craters cutting the fractures. You see fractures cutting the craters. And so these are recent, maybe even ongoing. I can't remember why I put that in there. I guess just to explain the geometry of the faulting. But let's jump ahead to something completely different now. So this is Aracoth. this is a much smaller body. It's maybe, I think 20 odd miles long, 35 kilometers long end to end. This is a planetesimal. And what a weird shape. It's actually even kind of weirder than a snowman. It's like two pancakes joined at the neck almost. And you can kind of see this. So, what we will do is we'll look at two images at once with stereo glasses. You guys don't have the stereo glasses handy, so I'm blinking them. But you can kind of get a sense from the blinking image on the right how flattened the larger lobe is. And we can tell that the backsides must be flattened too, because looking back at high phase, we could see Aracoth moving through the star field. And if you map out where the stars were occulted by the dark part of Aracoth, the red spots in that lower plot are where there should have been we should have seen a star, but we didn't see it. So Aracoth was in the way. And so you can also kind of tell that it must be fairly flattened just based on projecting the geometry and where it blinked out the stars and where it did not blink out the stars, which is the yellow spots. All right, so let's talk a little bit more about planetesimal formation. This has kind of been a big problem, and there's really been a paradigm shift that's kind of exciting for the scientists that are studying this. And so I want to tell you a little bit about it just because it's kind of a cool story. So, everybody's comfortable with, a disk of gas and dust forming around a newborn star, and we have pictures of them. These are some of my favorite Hubble pictures on the right, showing an edge on one of these disks where the dust is basically blocking your view of the star. The color image, which is the one to the left of the two Hubble images, is visible light, and you can barely see the star at all. The one to the right is more infrared, and the more the starlight makes it through the dust in the infrared. But what's going on inside of this disk ultimately is planets. But how does that happen? So everybody's okay with dust particles sticking together and making bigger things. And, you could imagine just taking that to ad infinitum and just gradually build up planets. But it really croaks by the time you get up to something like marble or walnut or grapefruit size. And the reason is that by the time you're that large, it wants to be in a Keplerian orbit around the star. But there's all this gas in the disk, and the gas is supported by gas pressure. So it wants to go slower than Keplerian speed because it's partially supported by gas pressure, and it doesn't need the gravity it doesn't need to move as fast to be stable. So any time a particle grows to this kind of pebble size, it starts to feel the headwind from the gas, and it just spirals into the sun, and you lose it. So that's been a frustrating problem. Is like, how do you get past that size barrier without just losing things spiraling into the sun? And relatively recently, people have been talking about a dynamical instability. It's actually an aerodynamic instability it's an interaction between the gas and the dust, and it tends to form clumps of dust, sort of like dust bunnies. And if those clumps can grow large enough to where they're gravitationally unstable and they just gravitationally collapse, that collapse happens very, very fast, on the time scale of 100 years or 1,000 years, which is fast enough to win against the everything spiraling into the sun problem if you get the conditions just right. And so the bluish plots, the three in a row on the right, are simulations of a small box in the nebula where there's gas and dust, and the density of the material is, I guess, lighter colors are more dense for the solids. And so you're stepping forward in time to the right. And why don't I show an animation of this just so you can kind of see, but basically clumps are forming and collapsing and doing it pretty quickly. So this is, and again, this is a small box selected out of the nebula. The sun would be way, way, way off to the left. And the Keplerian direction of motion is from the bottom to the top, going around the sun. And further away from the sun is to the right. And we're looking down on the disk of the nebula. So now I'll start the animation. And you can see that very quickly, clumps form these reddish spots that are big enough to gravitationally collapse. And this model doesn't have the resolution to follow the progression beyond that, but what's happening is you're almost instantly forming one or a clump of planetesimals inside each of these reddish spots. And so basically, Aracoth is what you get, or it's one outcome of this. You probably get wide binaries if there's too much angular momentum. You get tighter binaries if there's not that much angular momentum in the clump that's collapsing. You might end up with triple systems or quadruple systems that are dynamically unstable, and they eventually kick out the extra ones. But it looks like planetesimals sort of happen very abruptly. And that's different than the sort of very gradual dust addition kind of scenario that people were talking about 20, 30 years ago. So this is a real change of perspective. So once you've got a binary, like in the bottom left cartoon, how do you get it to join? You know, what kind of collision speeds are acceptable? And I'm going to show you a simulation of one that was too fast. Boom. And this was 10 meters per second. So this is not super speedy. I mean, you drive that fast through a school zone and you're not going to get a ticket. You could go that fast on a bicycle. You'd want to be wearing a helmet though. But it's just catastrophic when two objects collide at that speed. But you can do simulations, and by the time you get down to maybe about 3 meters per second, you can stick two objects together without of the size of the lobes of Aracoth without destroying them. So it seems like it had to be a very, very gentle merger, and you know that's 3 meters per second is like 10 kilometers per hour or 6.5 miles per hour, so pretty darn slow. You would live if you bumped into a wall or a concrete wall at that speed. So the other thing to talk about is the context of the various different populations out beyond Neptune. So a lot of this is in the framework of the Nice model, named after the French city, which is probably about 15 years old now. And the idea is that, as in the left panel, the original configuration of the solar system was a large belt of planetesimals, the white spots, and the giant planets in a much more compact configuration than their current setup. And eventually some instability happens. The giant planets migrate out. They throw the little planetesimal leftovers all over the place, basically get rid of most of them. Some of them end up in the Oort cloud, some end up crashed into Jupiter, crashed into the sun. Some are free floating through the galaxy, but there's way fewer of them than there was initially. And you end up with the solar system, something like it is today, with the giant planets much more widely spaced and far fewer little guys. And there's, you know, a bazillion variants, because theoreticians, every time they make a nice model, an observer will come along and make an observation that breaks the model. And the theoreticians are like, no problem, back to the computers, and they come up with a new variant. So by now there's many different variants, and including some that started with 4, 5, 6 giant planets. And sometimes one of those is still out there somewhere. Sometimes it's kicked completely out of the system. So, you know, if you want to imagine that there's an additional planet X or X, Y, and Z out there, this is a good excuse for it, but those things haven't been found yet. So now thinking about this planetesimal disk, you can imagine that there's some gradient, you know, with the chemistry changes as you go to colder temperatures further out. And so I've drawn redder things further out, whether that's right or not, whether it's a smooth gradient or whether there's abrupt changes where some new species condenses, like a snow line, who knows. But Neptune comes along and migrates out and disrupts all of that, and throws things around. Some get collected up into resonances, but there's still this outermost thin disk, which is called the cold classical belt. And that's the things that are still in circular orbits, still low inclinations. They haven't really felt Neptune's influence much. And conveniently for New Horizons, that's where the spacecraft went. So it was one of those that we were going to encounter. And Aracoth is a typical member of that population. They tend to be much smaller than the other Kuiper Belt objects. Pluto would be one of the largest ones on here. And there's everything in between, so Aracoth is sampling this outermost population, whereas the excited populations formed closer into the sun over a pretty wide range of heliocentric distances, and Pluto represents that. So Aracoth is not a building block of Pluto. It's a building block that didn't get used to build something big because either the dynamical timescales were too slow out where it formed, or there just wasn't time to build big things, or things were too sparse to get together and build big things. But the big things happened closer in and then got perturbed by Neptune. Probably a bunch of them crashed into Neptune along the way. One of them is probably still in orbit around Neptune in the form of Triton. Uranus is totally tilted over on its side, probably also due to violence from this early episode. All right, so what's Aracoth made out of? This is the raw data that we use to get compositional information. So you can see Aracoth bouncing around as the spacecraft fires its thrusters to keep Aracoth in the field of view. Each column in this image is a different wavelength, starting at 1.2 microns on the right, out to 2.5 microns on the left. And so as Aracoth marches through this scene, you eventually see each piece of the surface at each wavelength, and you can stitch it together into a spectrum. The spectrum is pretty low signal to noise, so what I did was in this spectrum, oops, I went the wrong direction. What did I do? Try that again. So this is just an average spectrum over the whole body, just to get better signal to noise. And the points on the left are from the color camera, and what they show is a red slope. You see the little spectrum down there showing where the human eye is sensitive, and it's more reflective at redder wavelengths. So that's what I mean by red slope. That's indicative of complex organics. Complex organics seem to be kind of ubiquitous in the outer solar system, so no real surprises there. And that red slope continues up into the infrared, and then by the time you get up to the smaller points, it's mostly flattened out. And water ice, which is very common in the outer solar system, has pretty strong bands where those two cyan arrows are, and we don't really see any evidence of it. There's a couple little dimples where those yellow arrows are, which is methanol ice, which is interesting. Not such a cosmically common ice as water, but it's clearly there. I'm going to show you a spectrum of a Centaur object, which is a refugee from the Kuiper Belt that's now crossing the giant planet orbits and is eventually going to turn into a comet or get kicked out of the solar system or something, called Pholus. And there you can see, well, the spectrum is pretty crappy at 1.5 microns, but at 2 microns, you can see the water ice band, and it has even deeper methanol ice bands. But that's what the water ice should look like, and we really just don't see it on Aracoth. So that's kind of a puzzle. We think we have a story for that, but it could be wrong. When you have carbon monoxide ice and plenty of hydrogen gas, this only works when the carbon monoxide ice is frozen. You can add hydrogens to it, and you gradually build formaldehyde and then methanol. And the outermost part of the disk, as you can see in the cartoon at the bottom, at the left, the carbon monoxide is in the form of ice. It's that cold. And the models to the right are models just showing where the dominant carbon carrier is and whether it's frozen or not. And I don't know if that model is actually, well, it changes as a function of time. I don't remember. So this is at 1 million years. And there it looks like the methanol ice doesn't start until 70 AU or so, but there are other times where it could come in closer. So that might be a hint of when Aracoth formed, but there's a lot of parameters that are unknown about the nebular conditions. So I wouldn't take this too seriously, but it does seem plausible that you could end up with these really oddball methanol-rich objects way out in the outer edge of the solar system. So to go to the big picture for Aracoth, I think this shape really crystallizes our thinking about this process of forming planetesimals, where you get this various instabilities that collect enough solids, I guess I should call them pebbles, together to where they can gravitationally collapse. And this is what the aftermath of that gravitational collapse looks like. And it hasn't really been cratered that badly. So this is, 4.5 billion years later, still what it looks like. Unlike in the asteroid belt, where things have really been pretty banged up, and the shapes that they have now may or may not have much to tell us about the shapes that they originally had. It's got a apparently weird surface composition, very, very low bulk density, because if it had a bulk density as high as, say, water ice, like 1 gram per cc, it would crush its own neck, just the gravitational attraction of the 2 lobes. And the fact that it doesn't do that tells you that it's got to have a pretty low bulk density. Now, unfortunately, these aren't the things that, the giant planets or even small icy planets like Pluto are made out of, because these are another thing that's even further out. But that process of forming the planetesimals probably happened throughout the solar system. And so this provides us a glimpse of the aftermath of that process. And so I'm going to go to give you guys plenty of time for questions now, because I hope I provoked a bunch.
Will, thank you very much. That was a fascinating talk and given us lots of things to think about. So could I ask you to stop sharing your screen? And
Absolutely.
We can see who's actually wanting to ask questions and the rest of it. And I'm going to hand over straight to Jeff Greenspan, because he's been desperate to ask you a couple of questions. Jeff.
Oh, thank you. So to summarize what I gather, you've answered a couple of questions I put in chat. From what I gather, your conclusions would be that Pluto does have recent or maybe even current tectonic and or volcanic activity, and that there might be evidence for a liquid water ocean under Pluto. That would be one hypothesis. So let me ask 2 geochemical questions related to that. The glacier you talked about, Sputnik Planitia, has these heat convection cells that, to my knowledge, are unique for any glacier in the solar system. And what I'd like to know is, what does that tell us about Pluto's formation and development? And the other related question to the glaciers and the nitrogen layering, do you think the compositional structure found on Oumuamua is reminiscent of the nitrogen layering and nitrogen glacier on Pluto? So those 2 questions. And thank you for an excellent talk.
So on the Oumuamua one, so there was a recent paper that I think it was Steve Desch maybe was involved with it at ASU, where they speculated that it was basically blasted off the surface of a planet like this and was very nitrogen ice rich, and they could account for all of its non-gravitational accelerations if it's very small, very bright, and shedding nitrogen, basically to provide rocket power. So that certainly has been conjectured. I haven't worked on that myself, so I don't really know if that's how feasible it is in terms of, what are the odds that the first interplanetary, or the second, no, it was the first one, wasn't it? The first one that we see is such an exotic material. Is that material actually quite abundant, or did we get just very lucky? Or is it that there's a preference to seeing something like that because it's spewing material, and so it makes itself more visible, or it's very high albedo. Those are questions I have that I can't answer. Now, getting back to the question about convection in Sputnik, one thing that helps is that nitrogen ice is both very mobile, and the molecules don't stick together very well, so they're easily mobilized. It's also a great insulator, thermal insulator. So if you're putting even a feeble amount of heat into the bottom, it's not crazy to start a convection cell happening. And that's been modeled. And if it's, a few kilometers thick, you could get convection cells on that spatial scale. And the amount of heat that's coming from Pluto's interior, even if there isn't an ocean freezing, if there's only just basically chondritic rocks with uranium and thorium and so on breaking down, just giving off their natural radioactivity, it's still enough heat to drive this. So there's nothing that offends physics or sensibility there. Did that answer your question?
Yeah, thank you very much.
Thank you, Jeff. Can we go over to Pete?
Hi, well, excellent talk. Really enjoyed it. I do have a question. Where is New Horizons heading? Is there another candidate for an encounter somewhere in the Kuiper Belt?
Yeah, so New Horizons is now actually out at about 53 AU. So it's basically past the classical Kuiper Belt.
Yeah.
So it won't be a classical Kuiper Belt object if we find another one. The time to search is the summer, Northern Hemisphere summer, just simply because that's the direction it's heading. That's what part of the sky is up in the Northern Hemisphere summer nights. And so there's a very intensive search going on right now. And it's all a question of probability until you actually find one. So right now the probabilities are probably not in our favor, but they're not hopeless. And so we're trying. And we think, so there's a spray of stuff that goes out much, much, much further. And if we can discover something that we could encounter out at 90 AU, that buys us a lot of time.
Yes, yeah.
To where a relatively modest impulse will get the spacecraft there. If you do the burn soon and then wait a decade, that buys you a lot of space. So there's I would say a decent but no sure thing chance that we could do such a thing. And we're going to keep trying, and we're in the process of writing a proposal to NASA right now to buy us 3 more years to try, after which we would give up and just use the rest of our fuel to do other science, like the Voyager spacecraft are still doing today.
Right, yeah, okay. I have another question. The Kuiper Cliff, is this something that actually exists? I mean, I have heard of the term observationally that the density of objects abruptly ends at around, is it 55 astronomical units or something like that, or is it just?
Yeah, so it's a problem of coupled, everything's getting fainter as you go further from the sun, because you've got the R squared to light it up, and then you've got another R squared to look at it. So things are falling off really quickly in terms of their brightness. But the size frequency distribution can also be changing. And clearly the size frequency distribution of the cold classicals is different than the things that formed closer, because they're smaller. You just don't have big cold classicals. So if the size frequency distribution continues to shrink, we would not have been able to detect them yet. And so that possibility is a real one. And new telescopes, JWST is going to launch in 2 months now, 3 months, whatever, I think it's December now. And it would have the ability to see a fair bit fainter. And so there's already a program that's been approved to search deep in the plane of the ecliptic with JWST and see if there's an extension.
Yeah. Okay.
And of course, if that turns out to be true, then that means that New Horizons has a decent chance of getting to one as well.
Okay.
So I would like it to be true, but we'll see.
Okay, I understand. Great. Thank you very much.
Thank you, Peter. Catherine?
Okay, you mentioned in one of your diagrams about solar production from the UV light. Would that mean that it would be possible to get solins around by Titan going around Saturn and increase the possibility of life in the solar system?
Yeah, so these solins seem to happen quite easily. And I don't know that we need the tholins to form life, for instance, on Earth, because there's lots of ways to make organic chemistry. But they certainly don't hurt. They're they have all of the functional groups that you find in proteins and biological molecules. And they're actually kind of toxic for that reason. And so, in fact, a friend of mine has a little bottle of tholins that he always takes with him to meetings. Nobody's ever asked him what that is when he gets on the airplane, but it's like you would not want to open that bottle up.
Okay, Catherine.
Thank you very much.
Okay, Mick Nichols. Mick?
Yeah, I was just trying to unmute. You know the first image of Pluto, what you showed, where you zoomed in and moved about? All the colours on there, is that the actual colour of Pluto?
No, and I should have been honest about that up front. So the color camera has 4 filters, and 2 of them are at wavelengths that the human eye could see, and the third one is out in the infrared. And what we did was we put the shortest one into blue, the middle one into green, and the infrared one into red. So this stretches the wavelength range of what the human eye could see. So we've done our best to try to make a true color version, and it looks blander. I mean, it looks sort of like shades of brown sugar, ranging from highly purified sugar to molasses. But that whole spectrum, sort of from very dark brown to medium brown to white. Whereas when you fold in the infrared light, it sort of broadens the color spectrum. And so I apologize for not saying that up front. I should have, but you see more when you have more wavelengths to throw at it.
Okay, Mick. And back to Jeff. Jeff Greenspan.
Thank you. A couple of Kuiper belt questions. One is the observed clustering of objects in the Kuiper belt a statistical anomaly due to small sample size, or do you believe it's potential evidence for a Planet 9? And the second question is, can you discuss the hydrogen wall that New Horizons detected at the boundary of the Kuiper belt? Thank you.
Okay, so the hydrogen wall, I don't think New Horizons has really detected it so much as other space missions detected it, and we are looking in the same directions to see what we can see. But so this is related to how the solar wind is expanding and forming a bubble, but the sun is moving with respect to the local galactic environment, and so we have kind of there's a streamline of magnetic field and galactic material that sort of drapes over the bubble that's blown by the sun. And yeah, there's this zone where neutral atoms are streaming in, that's this hydrogen wall. And I have to admit, I don't really study that. So I'm not really sure what the physics is of why that looks that way. But a bunch of the people that are involved with the particle instruments on New Horizons are very heavily involved with that. And so I'm afraid I'm gonna have to punt that question. But your other question on the clustering, that is an area of intense debate right now. So part of the problem is that when you're looking for Kuiper belt objects, you're taking a picture in some random direction, maybe not random. And what you would see there depends on what dynamical orbit it's got. So for instance, if you looked in the direction of the Neptune Trojans clouds, you would have a decent chance of spotting a Neptune Trojan. But if you looked in some other direction, you would have a very low probability of spotting a Neptune Trojan. And so if you did your survey in the wrong direction, you might be blissfully ignorant about Neptune Trojans, whereas somebody else who did their survey in a different direction would have detected a bunch of them. And the same is true for all of the dynamical classes that are resonances with Neptune. So the Neptune Trojans is a 1-to-1 resonance with Neptune, but the 2-to-3 and the 3-to-4 and the, 7-4, and all of these other resonances are populated. And so what that means is that they're at perihelion at certain places with respect to Neptune. And so if you didn't survey, you would not know about them. And so you have to really do a lot of statistical work to try to tease out what you can truthfully say based on a given survey, based on where it was pointed, and so on. And so one problem is that the Milky Way is blotting out 2 big chunks of the ecliptic. And if you're trying to discover Kuiper Belt objects, you don't want to look there. So there's big regions of the sky that people have basically avoided because they're just too cluttered. And, you know, why would you beat yourself up looking for Kuiper Belt objects there when you can pick a nice clear piece of the ecliptic? And so the real question is, are the biases that are introduced by the non-random distribution of where people searched the explanation for this apparent clustering, or is that clustering real? And I would say the jury's still out on that. I've seen papers arguing it both ways, back and forth. So it's still a very exciting question, but I don't think, you know, maybe the answer will be when somebody discovers this object. Well, okay, if it's there, no arguing with that. But right now, I think the community is far from consensus.
Thank you very much.
Okay, ladies and gents, I'm still looking for questions. Roy Gunson.
Yeah, what I was interested in is that Aracoth is a double load object, and more and more we're discovering quite a lot of body. I mean, the Rosetta comet was a double lobe object, and is this like an indication of the common mechanism of creation? And also, looking at Aracoth itself, the larger body, it seems to be made up of round hummocks, as if it's been built up of smaller round objects, as it were, that's built it up.
Yeah, I think both of those things are true, and they're telling us something about the process of this gravitational collapse, which may be something of a hierarchical collapse, where you maybe initially form these sublumps, and then those sublumps come together. I mean, part of the problem when you're trying to collapse and form an object is that you often end up with excess angular momentum. And so bifurcating into lots of little objects that then dynamically interact, and some of them get kicked out and can carry off the excess angular momentum, allows the remainder to come together. The other piece of the dynamics is that all of this is happening while there's still gas in the nebula, because you need the gas and the dust interaction to get these clumps to form in the first place. And so the gas drag also helps things come together relatively gently. But I totally agree with you. I mean, that large body of Aracoth looks like it's formed from maybe, I don't know, 6, 7, 8 lumps that came together violently enough that they're mostly smeared out and formed one sort of coherent body. And then the last piece got glued on very, very gently later. And I think the best scenario for that is that the violence of the coalescence of the large body, the large piece of Aracoth, was probably a little bit higher. So maybe that happened earlier in the collapse. And then the head joined in through a very slow spiral in with gas drag or something like that. But yeah, I would love to see a dozen more of these to just see if they always look that way, or if sometimes you get things happening in a different order, and you know what the different outcomes are. You know, it's very tantalizing seeing one, but until we get to see a few more, we're going to assume they all look this way, and that's probably fooling ourselves.
Okay, back to Mick Nichols.
Yeah, one of the things I've always wondered about Pluto, we know that when solar systems are forming, there can be very violent places. Things get destroyed, things get thrown out. Speculation that Earth might be a second-generation planet. All of these gravitational interactions, could that put Pluto into the orbit it's in, rather than it being a Kuiper Belt object? Because it looks very planet-like. It's, you know, it's round. It's not very irregular. or even more intriguing, is there any possibility it could have been thrown out of another solar system into orbit it's in now?
Yeah, these are good questions. So in the NEAS model scenario, there's a disk of planetesimals that didn't quite make it into giant planets. And the closer you get into the sun, the faster the dynamical timescales are, the higher the density of material. So the speculation is that there's relatively large objects getting formed just beyond where the giant planets formed. You just didn't quite make it to large enough to capture gas from the nebula to be a giant planet. But, Pluto and perhaps even larger objects might have formed in the thousands in there. And we're left with now only a handful of them. Eris is a good example, which is much further out now, but it probably also formed in that same general area. I totally agree that it's the dynamical interactions, these sort of crazy stochastic random interactions that put Pluto where it is now. I think it probably formed closer to our sun and not around a different sun. I think things in the Oort cloud are better candidates to have formed around another sun, just because they're so far out and they get perturbed around so much. Unfortunately, we only get to see them when they come in as a comet, because they're just too far away. So I'm torn between, which is the most important follow-up. Is it to go back to Pluto with an orbiter and really do Pluto right? Or is it to go and visit Eris and Makemake and its other kin, and see what they have in common and what's different about them? Boy, I'd love to do both.
I'm going to take 3 more questions. Catherine first. Catherine, can you unmute yourself?
Yes. Does your clumping model include electrostatic charge?
So that has been invoked as a way to try to get beyond that spiraling in problem. If you could use the electrostatic charging to actually grow up to where it can be gravitationally bound together, then once you get up to a kilometer in size or so, you can deal with the headwind, because you're the bull in the china shop. You can take it. So it's really a question of getting from this pebble size up to maybe a kilometer size. And I've seen people try to do that with the electrostatic forces. I am a little skeptical that really works. The electrostatic forces certainly help in growing the pebble-sized things, because if you run 2 dust lumps into each other, it's those electrostatic forces that are holding those little tiny particles together. But I don't think that gets you to the planetesimal scale.
Okay, Catherine. And Jeff Greenspan. This is your last one, Jeff. Unmute yourself, Jeff. Can't hear you.
Sorry. Thank you very much. On your surface pictures of Pluto, I deduce, at least from what I can see, that there are mainly 2 types of indentations. I see some rather decently sized craters and some small pockmarks that you claim are really from internal eruptions. My question is, the absence of small-sized craters telling us something about the size range of objects in the Kuiper belt? Thank you.
Yeah, so there was a study done on that led by Kelsey Singer a couple years ago, and to be honest, Sharon is the better object to use for crater counting, because the conjecture is that it doesn't have ongoing resurfacing, muddying the water, as it were. And there certainly are small craters. You see them, but they're less abundant than might be expected if there was, so in the asteroid belt, if you have this collisional cascade where, you crash one object into another object and you end up with 20 next size down, and then when those crash, they make 20 more each, and you end up with this power law with just zillions of little objects for every one big object. That power law doesn't really work for the crater counts at the small size end on Pluto. It really looks like the low size end of the craters on Pluto, well, on Sharon mainly, is depleted. Now, it doesn't mean that they don't pick up again at an even smaller size range that we can't really see in our images because the pixels weren't small enough. But it does look like there's not this similar cascade of fragments that you see in the asteroid belt. I think it doesn't mean there aren't small fragments, but the typical small Kuiper belt object that we see from Earth is probably a planetesimal and not a fragment.
Thank you. And thank you for your excellent talk.
Thank you. Last question then goes to Peter Lloyd.
Oh, thank you, Paul. I think so. You said that some of the disturbances in the outer part of the solar system could be caused by the outward migration of Neptune. Did I understand that correctly?
Right, right, and there, that actually throws up an interesting question too, which is what Neptune's doing as it's migrating out is it's stealing angular momentum from the small bodies.
This was the nature of my question. Really, I've never understood how major planets can migrate outwards, because where does the energy come from?
Right, exactly. No, this is a great question, and it's subtle, because there should be this time irreversibility. If the solar system consists of small bodies and Neptune interacts with a small body, it could take some angular momentum from it, but chances are it's going to encounter that body again, and just as likely the angular momentum flow will go the other direction. Right. So the trick is that Jupiter plays a key role, because Jupiter is massive enough to actually throw something completely out of the solar system. So Neptune scatters things around, on average feeds them down to Jupiter, and Jupiter kicks them out, so Neptune never sees them again. So Neptune is net stealing their angular momentum.
So it's stealing it from Jupiter in that case, because Jupiter loses angular momentum if it's throwing things out of the solar system.
That's a fair point. Yeah. And so Jupiter is actually going into the sun to push Neptune out.
Right.
Is yeah, that's right. That's the final who wins and who loses. But there's an interesting piece of this, which is that Neptune is where it is today, and if the planetesimal disk continued out, why did Neptune stop where it stopped? Because there's this infinite supply of more bodies. Why didn't it keep chewing through them and go further and further out? So that's a hint that there's something changing in the planetesimal disk at 30 AU. And you noticed in the NEAS model, their original scenario is that the planetesimal disk just stops at 30 AU, and that's why Neptune stops at 30 AU. Now, the cold classical belt is obviously beyond 30 AU, and it's in orbits that never got perturbed, so it had to form where it is. But are they just that much less abundant and that much less mass that Neptune didn't really notice them out there? There's definitely questions that we haven't figured out yet, but that's one that's, I think, a really interesting one.
Is it possible that actually Neptune is still migrating? It's just that it's going very slowly, and it hasn't moved a measurable amount since we first discovered it.
I guess that's a fair point, because things are still getting fed down into the inner solar system in the form of centaurs and then comets, and some of those Jupiter will kick out of the solar system. So I guess this process is still going on, but not enough that we need to worry about it in terms of navigating spacecraft. Neptune moved.
Oh, thank you.
Thank you, Peter. Just one last question about New Horizons itself, Will. If you find an object and you can make your course corrections, etc., what's the lifetime of the spacecraft?
So, of course, the Voyager spacecraft are still functioning today, and they were launched in the 70s. We didn't get launched until the early 2000s, no, mid 2000s. So really the way it works is you slowly turn things off so you can keep the spacecraft alive. And as long as you've still got the computer running and the transmitter, you're a functioning spacecraft, because it can operate itself and it can phone home. Once you have to turn off one of those two, you're done. And we can probably keep that going until probably into the 2040s. Now, you'd like to actually have an instrument on and maybe actually make some measurements. So that makes it a little trickier, but you can cycle through things and turn one on and then turn a different one on. The engineers are really amazing at coming up with clever strategies to keep things limping along. And I would suspect that we could keep it going well into the 2040s.
So will you be still working with this machine when you retire?
Probably not me, because my expertise is not the stuff that, basically the Voyager spacecraft are essentially heliophysics and interstellar physics. And I don't do that science, charged particles and magnetic fields and so on. So we would hand off to a new generation of people that would be doing that kind of science.
Okay.
Plus, I'll be pretty old by then.
Okay, well, thank you for an excellent talk and for joining us. Just leaves me to say, ladies and gentlemen, can we give Will Grundy a big Mexican Swinton Astronomical Society? Thank you. Thank you very much, Will.
Thank you.